Okay, so what do we do in those cases? How do we replace sigma in this formula? So what we do is to use the standard deviation of the sample. And remember, how do we estimate the standard deviation? That was a long process that we review in lecture 3. We basically studied how to estimate the deviation from the mean. Later, we use the variation. We take the square root of that variation. We had many different steps in order to get there, right? But in this case, it's important to highlight that the standard deviation of the sample is affected by something that is called the degrees of freedom. So the degrees of freedom are a statistical property according to which when you want to estimate a statistic of a sample, you need to, so there is a formula, like you need to subtract the number of parameters that you want to estimate about that sample from the sample size. In this case, that I said that we have a sample of 100 individuals, and we want to estimate just one parameter, which is just one parameter. So we have a degrees of freedom of 99. So imagine that we have the standard deviation of the sample, right? That we need to estimate here. In this case, is something that we don't know because we don't have that information here, is the summation of the square deviations, and we divide that by 99, not by 100, which might be the normal thing that we should do with the population. But because of this idea of the degrees of freedom, we need to do it by 99. Okay? Okay, so there's a new complication. As the sample approximates infinity, we can use the normal distribution. So the larger the sample, the more confident we are to use the normal distribution. But when the sample is small, the properties of the normal distribution don't work very well. So what can we do when we have a small sample? So there is something that was created to solve this problem, and it's called the student's t-distribution. The student t-distribution is another kind of symmetrical and unimodal shape of a distribution. But in this case, the how can I say, the way that we interpret those results of this distribution vary according to the degrees of freedom that we have. Okay? To some extent, the idea is that with a t-distribution, we're going to have more dispersion than with a normal distribution. Okay? Look at here. So we're going to focus on this level. This is when we have to have under the area under the curve that we want to have here is usually so to some extent what we want to say is that we want to have precision, and we want to know that we are only excluding the 2.5% of the potential cases. So remember that the 95% of our observations are within the range of more or less 2 standard deviations, right? So what is excluded from that area is what is here, what is not included in the curve, right? So in that case, when we want to estimate and we want to exclude just the 2.5, so we want to be confident about the 95%, if we have C values, we multiply the standard error by the 1.96, okay? But with the t-distribution, we cannot do that. We need to go to, or that depends on the degrees of freedom, okay? If I have very low degrees of freedom, I need to multiply my standard errors by 12.7, which is very high. So in other words, when I don't have high degrees of freedom, what I'm gonna have is a lot of dispersion in this case, okay? the dispersion is going to be very high, the standard error will be very high, and my precision about the estimation is going to be very low. I'm not going to be precise at all, okay? But when my degrees of freedom increase, for instance, when I have 2 degrees of freedom, so I'm going to have much more precision. And there are values such as 60 degrees of freedom in which I almost have the 2 standard, like the same value of the 2 standard deviations. And with very high levels of degree of freedom, for instance, when you have a value of 1000 degrees of freedom, the value is going to be very close to the normal C. Okay. Let me show you this. This is probably better to illustrate this idea of how the t-distribution and the normal distribution are related. So as you can see here, the degrees of freedom affect the shape of the t-distribution. The t-distribution is perfectly symmetrical and is unimodal, but the extent or the way that you can use the t-distribution to make predictions will vary according to the degrees of freedom. Okay? So, for instance, when you have only 1 degree of freedom, there's going to be more dispersion, right? And when you have almost 1000, or when you have 1000 degrees of freedom, your precision is going to be higher, and it's going to be almost similar, or it's going to be basically the same as the normal distribution. Okay? In this case, it's not, this figure doesn't show that dispersion as in the table, but it's to some extent the idea that we want to, that I want to give you about how the normal, the t-distribution, I'm sorry, varies, and when you have very low degrees of freedom, you will have much more dispersion. Okay. Okay. So how do we interpret the results with the t-distribution? It's to some extent similar to what you do with the normal distribution, but the difference here is that you need to pay attention to the degrees of freedom again. So similarly, you're gonna have the mean of the sample, in this case is again 55.2, and you're gonna add, in this case, your degrees of freedom are 99. Then you need to go to the lowest number close to that one, which in this case is 90, and for that reason you need to multiply by this number 1.98, right? Instead of 1.96, which is in the case of the C values, you're gonna multiply by 1.98. So it's very close because you have very high degrees of freedom here, right? And you have that value and you multiply, and that's gonna be your upper boundary. And your lower boundary is gonna be very similar, basically the same, but you just subtract this value from the mean, okay? So basically what you have here is a high range, not super high because your degrees of freedom are fine, but it's gonna be higher because of the these degrees of freedom, but also because of your variation component also change. Okay, in this case is 2.14, and in the past it used to be 1.72, I guess. So you're gonna be less confident because you don't know sigma. Okay, that's to some extent like the bottom line here. Okay, so let's summarize until here. So we have said that we want to estimate the population parameter, but we don't know how to estimate the population. No. We cannot be certain that the population parameter is just one number, so we provide like a confidence intervals or a range of values that we feel comfortable to say that the true population parameter is within those boundaries, right? If we have a very large sample, we can use the normal distribution. If we have a small sample, we can use the t-distribution. And as the t-distribution increases, the size of the sample is going to be more similar to the normal distribution because the degrees of freedom is going to be higher. So we have new elements for our notation. We have another term that is this random sampling error. Now we know that the random sampling error is like a factor of the standard deviation in the population parameter divided by the square root of the sample size, right? When we have that sigma, the value of sigma. When we don't have the value of sigma, that random sampling error will be equal to s divided by the square root of n, okay? And we also introduce this idea of the confidence intervals that will be equal to x bar and more or less 2 standard errors, okay? Okay, so we have learned how to use the normal distribution or the t-distribution to estimate the mean of a numeric variable. But what can happen? What can we do when we have a qualitative variable, such as a variable that is in the ordinal or the nominal scale of measurement? So maybe we cannot use inferential statistics to these kind of variables. Well, we can do something. We can use what is called the sample proportions. Sample proportions are the number of cases falling into one category of interest, a certain variable, divided by the number of cases in the sample. Okay? So imagine, for instance, that we want to ask people, I don't know, if they support the president, whatever, and they say yes or no. Those are the two categories of that variable. So we want to estimate the people who say yes. And what we do is to count the number of cases of yes divided by the total cases, okay? And we want to estimate what is called Q, which is basically P minus 1, okay? I'm sorry, 1 minus P, so the rest of the cases, okay? So with that in mind, we can not only estimate P, which is the value of interest here, which is the sample proportion, but we also can estimate the random sampling error. The variation component will be this like the square root of the proportion of our category of interest, which is P, times Q, which is the rest of categories, okay, divided by the square root of the sample size, okay? And the interpretation is the same that we have done in the past. So we provide our 95% confident interval, and we provide these two boundaries, the upper boundary and the lower boundary, and it's the same. So you have the p-value and you add 2 standard errors, or you subtract 2 standard errors, okay? However, there is a caveat with this kind of method because a proportion is already bounded between 0 and 1. You cannot have more than 1 because that's not possible. So you are dividing a certain sample by 100. So you have 100. So you can have 100 chance of somebody of the sample saying yes, we support the president, or we can have 0, but you can have more than 100, right? Or in this case, you cannot have more than 1, a proportion of more than 1. For that reason, when you have values that are very close to 0 or to 1, the applicability of this sample proportion is lower to some extent. We don't have the same applicability in this kind of cases, and there is a rule of thumb of how to know if what we have might be problematic to use the normal distribution, and is that you multiply the value of P and the value of Q by the sample size, and if both numbers are higher than 10, then you're fine, you can use the normal distribution, okay? So we finish here with the notation. We have P and Q when you want to use sample proportions. we have here again the confidence intervals. So again, we have the size, the mean, the standard deviation, the random sampling error. Okay. Okay. So just as a summary, so we learned that it is critical to use random sampling to eliminate systematic bias. Otherwise, we cannot apply these inferential statistics, or at least with surveys, it's impossible to do it. So you're conducted a poor survey if you haven't used this random sampling. And okay, so imagine that you have this random sampling, so you eliminate systematic bias, but you introduce random sampling error or a standard error. Okay. And there are different situations. In one situation, we know what is sigma, and sigma is the real standard deviation in the population. And we estimate the random sampling error with this formula. There is a second situation in which we don't know what is sigma. This is the most common situation in political science, at least. And in that case, we use the standard deviation of the sample. And the caveat here is that the standard deviation of the sample is affected by the degrees of freedom. So whatever is the size of that sample needs to be subtracted by the number of parameters or numbers that you want to estimate. And in this case, it's just one, which is in this case the standard deviation. And there is a third kind of situation in which you don't have a numeric variable but a qualitative variable. And in that case, you have this specific formula in which you need to divide the square root of p times q by the square root of the sample size. Okay, so when you have the random sampling error or the standard error to provide this population parameter, what we do is in the first scenario, we just subtract x from two standard errors. And we use the C values and the normal distribution properties. And the second situation in which you don't have the value of sigma, then you use the T distribution, and basically you do the same, but you pay attention to the degrees of freedom. If your degrees of freedom are very very low, then you probably have higher T values, and you're gonna have more standard error, and you're gonna have less precision. And as your degrees of freedom go high, then you're gonna have a sample that is very similar, a distribution that is very similar to a normal distribution. And your standard errors will be probably lower, okay? And the final situation in which you have a sample proportion, you just provide the value of P and more or less two standard errors. Okay, that's all. That's the basic foundation of inferential statistics. This is just to know where the rest of the things come from. But we're gonna use these to test hypotheses, basically, and to run a significant test and so on and so forth. So this is very critical. So if you have questions about these concepts, it is critical that you ask me those questions, because this is not a simple thing and the journey has been very long. We have covered many different things, and it's normal that you have probably questions about this topic, okay? So ask me those questions. Especially, I want you to feel comfortable with these ideas. First, the role of random sampling inferential statistics. Second, what is the central limit theorem? Third, what are the properties of a normal distribution, and how we use z-scores to standardize a sample, or the values of a sample of a distribution better in a sample, and in order to use the properties of a normal distribution. And when do we need to use a T distribution, and what are the difference between the T distribution and the normal distribution, and when the T distribution is similar to the normal distribution? Okay, and we also learn how to estimate, and we also learn how to to estimate these proportion samples when we have qualitative variables. That's the third topic. And finally, we learn how to estimate and interpret random sampling errors and the 95% confident intervals with both numeric and qualitative variables. Okay, so there are many topics, so please ask me questions. I know that there will be many questions. Thank you so much.